Okay, hello everyone. Today's speaker is David Jaz Myers from Topos Institute. So he's going to tell us about double categories and double categories, the algebras of coupled dynamical systems. So David, please take it away.
Great. Thank you so much for inviting me to talk here. So this is going to be a sort of report on an ongoing project to understand, I would say, the abstract algebra of general systems theory. And so I'm going to say more about that. So just oh, I got a lot of feedback right now. Sorry.
Is it
Uh,
because of us? Maybe should we mute?
someone is someone is feeding back. Um, thanks, sissies. Um, uh, yeah, so just a little bit of a history of this project. So I wrote a manuscript on using double categories to do certain kinds of dynamical systems theory from the compositionality of behaviors of certain kinds of dynamical systems. I'm going to go into that a little bit in this talk. Um, and uh, and then I, went and finished my PhD and did my postdoc in something else. And this is what I think how you know me from my time at the in the New York University in Abu Dhabi and Hisham Sati and her Schreiber's group. And now I'm back to working on this and with everyone at Topos. And so we hope to have a couple of papers in this program out soon. So joint with Sophie Libkind on it's going to be a paper which we're really hoping to drop quite soon on this, and then a sort of pure theory paper that's going to follow it up, which will fill in all the proofs, which is also joint with Sophie, Kevin Carlson, and Jason Brown. So that's sort of the a lot of this, and some of the work in here is also joint with Matteo Capucci, but I'll say that when it comes up. Okay, so the plan is I'm going to talk about a general approach to dynamical systems. There's quite a few approaches to understanding sort of the categorical algebra of dynamical systems. I'm going to focus on one of them where they are best expressed as lenses. And so I'm going to explain what I mean by dynamical systems. It's actually quite general, but this approach actually can get even more general. I'll sort of gesture at that at the end. But already it's going to be quite general, but it's also going to be quite specific, as in by dynamical systems, you're very happy to think of systems of parameterized ODEs. And we'll see also that POM-DPs, or partially observable Markov decision processes, also fit well into this framework. So if you're happy with systems of ODEs, or if you're happy with POM-DPs, then that's substitute when I say system, that's what I mean by system. But we're going to give sort of an abstract algebraic point of view on the coupling of dynamical systems. And we're going to express that as by saying that dynamical systems form a module over a symmetric monodal category of coupling laws, which we'll explain. So that idea really goes back to David Spivak, um, and his collaborators Patrick Schultz and Christina Vasilakopoulou, where they give operad algebras over wiring diagram operads. But we'll see that in a way as a module over a symmetric monodal category of coupling laws, where the coupling laws can sometimes be drawn if they're simple enough as wiring diagrams. But then we'll realize that this sort of point of view has missed one of the fundamental things you want to do in category theory, which is you want to map between your objects. So we'll look at maps between systems, and these will also compose in their own way. And since we're going to end up with two kinds of compositionality, one by coupling our systems and one by mapping between our systems, we're going to start to use double categories. So we're gonna describe these double categories of lenses, which will be the sort of mathematical object that underlies the systems theory here. And then we're going to spend most of the work here is going to be constructing these symmetric monoidal loose right modules of dynamical systems. So this is going to give the compositionality of the systems and their coupling laws together with maps between systems and appropriate notions of maps between coupling laws or compatibilities between coupling laws and maps. And this will give overall a whole notion of representability for symmetric monoidal loose right modules in the form of so giving a sort of Yoneda theory for coupled systems that recovers a number of behavior functors which have appeared in the literature and a number which haven't, and yet. And so this will be a general sort of part of the theme of it's often called applied category theory, or which I like to call categorical systems theory. So I did not actually put any future directions in there because almost surely we're not going to get there. But ask about it if you're curious, because there's a lot to talk about, in particular with assumed guarantee reasoning is where we're going next. So okay. So what's a dynamical system? Let's start with a particular example, the system of ordinary differential equations. No matter what field of science you're studying, you're almost always end up with a bunch of systems of ordinary differential equations that you want to solve. So we'll express a system here as a single vector equation, saying that the time derivative of the state vector is a function of the state vector and a vector of parameters. So we can encode that function of signature below, which is it takes n state variables and ns state variables and np parameters, and it gives us a vector of state displacements. And then also we're going to want to add a feature to this that is not present in most presentations of this stuff, but is sort of implicit, which is that you can also expose some variables of the state sort of to the environment. And this is not important when you're studying a single equation, but it is important when you come to study coupled systems of equations. So the way that systems of equations are coupled is by setting those parameters, P, as functions of the states of other systems. And so we will say that really you can't just set them as functions of the states of other systems generally. You can only set them as functions of the exposed variables of those states. So the part of the modeler's choice here is not just determining the dynamics in the form of the vector u, but the exposed variables in the form of the vector e. So so in total, a system of ODEs is going to be characterized by these two functions of this signature there. So we are going to box up that system. We can draw it in this way as a little box where the system UE is put into a box with NP many input wires, so that's the number of parameters, and NO many output wires, and that's the number of exposed variables. So we think of the system as this sort of a way of transforming time-varying parameters into time-varying exposed variables. So it acts as a little function that goes in that box, but it's a stateful function because it has actually the states that actually flow along the dynamics that are set by the parameters and the current state. And then I'm also going to give a notation there on the right, which I'm going to refer to many times, where for just how to write these pairs of functions. So we have u, which goes sort of backwards, and we have e, which goes sort of forwards here. And you can see, oh, there's a little typo. This should be trns, and that should be rns there. And wow, there's a number of typos. The outside one should be no and np. Excuse me for that. So now we can talk about how to couple systems. So the way we're going to couple systems is we're going to set some of the parameters according to functions of the states of other systems. So in particular here, I have two simple systems. They describe the population of foxes and a population of rabbits. So F is foxes, R is rabbits. And they have a birth rate. There are two parameters for each. They have a birth rate which is the first parameter, and a death rate, which is the second, or P1 minus P0 here. And now we can couple these up by saying that the foxes eat the rabbits according to some rate alpha, and the rabbits the rabbits provide nutrition to the foxes, which helps them sort of reproduce according to some rate beta. And so this coupling law, by which I'm saying how we're going to set which parameters according to which exposed variables, which you can see I've expressed as a sort of wiring diagram here with little function boxes on the wires. That coupling law gives us at the end, acts on these two systems, right, to produce a single combined system. With now, it has two parameters, but it also has two exposed variables, namely both the foxes and the rabbits are part of this coupled system. And as you can see now, internally what we have is that the foxes are born at a rate proportional to the rabbits, and the rabbits die at a rate proportional to the foxes. And so this is a way that we couple together two simple exponential models of population to get a more interesting Lotka-Volterra system of population dynamics, which is now periodic. So so that's what I mean by coupling systems of equations. And then let me tell you how that works sort of mathematically. But before I do, let me rewrite these two functions here in a way that suggests how you can do this in a coordinate invariant way. So more generally, we still think of the function E as from R and S to R and O. So these are our from the state space to the output space or the observation space. But now we can think of U. We should really be thinking of it as a section of the tangent bundle, a parameterized section of the tangent bundle. And the reason is that U ultimately is going to set the dynamics of our system. And so really the vector U is not a vector, not a point in state space. It's a tangent vector to the point in state space that you're already at. So it really has this type signature. And in particular, we can form this diagram above where we imagine that our parameters are bundled up over our observations, in this case, trivially. We pull them back to the state space using the exposed variable function, and then that gives us the overall space that parameterizes our dynamics. So in this case, as you can see, it's a pair of a state vector and the parameter vector. And then we map that into the tangent space. And of course, it has to be part of the tangent bundle. So that's my reformulation. And with that reformulation, I can formalize the downstairs notion as using pullback. So this is a bit messy because it's a bit completely overwrought, but it is fundamentally quite a simple idea. So what we're going to do is we're going to take that coupling law, which is in light blue there, and we're going to turn it into something that looks a lot like what the systems look like. It's going to be turned into one of these spans of bundles. So it's a very special kind of span of bundles down here, just here. And what that is on the bottom, well, if you look on the bottom, right, it's going to tell you what this coupling pattern does to the outputs. But this coupling pattern, if you look, it just sort of copies the inner outputs straight out. So we'll put the identity down on the bottom, and that's what it will be. Can you see my mouse when I move it? Sort of pointing at things.
Yes.
Great. So here, this is the identity. That says that I take the inner boxes here and their outputs, and I just copy them right out. So the function that sends the inner outputs to the outer outputs or observations is identity. Then I have to give a back pass here. And this one is going to tell me how the outer inputs and inner outputs, so you can see here, I formed this sort of pullback here, that is outer inputs and inner outputs, how they get sent into the inner inputs, which is this. Of course, the action on this R2 is determined by the fact that it has to live over as a bundle, so we can ignore that. It has to be determined by what it does on this component. And I've written that over here, and what you can see is what it does is it takes our pair of inner outputs, x1 and x2, our pair of outer inputs, y1 and y2, and it sets the inner inputs according to this matrix here, if you will. And that matrix, you can see, has this second parameter here and this first parameter here set accordingly to the outputs that it's reading. So this is agnostic to what you put in those boxes. It will always couple anything you can put in those boxes. But the way it couples it is precisely the way you ended up getting. You set the you can trace it back by saying you set the first parameter of this first top box here by, well, tracing it back. Oh, it's beta times this first output. And that is what appears in this component up here. Okay. Meanwhile, the first parameter here just, whoop, it takes the outer output, and that's why this one's a Y1, and similarly on the other box. So now what we have that, we can take both of our systems, and if you remember up here, I'll go back, the systems up here on the top, they correspond to these weird kinds of spans. It's just the exact same data as this, but I've repackaged it into this form of a span of bundles. And up here, I can take both of them and I can take their product. And this is the Cartesian product, in this sense, is acting as a parallel product of systems. So the Cartesian product is a dynamical system. It's a system of ODEs, but it's not coupled yet. It's just I put both variables and they satisfy both of their equations independently. And so that's what you see over here. But then I can compose this span here with the blue span. So the system, the parallel product systems here with the blue span, and I compose them as spans, namely by pullback. When I end up taking the pullback, what I end up doing, since most of these are just product projections, you sort of just reshuffle which things you're taking the product projection of. The resulting composite I get here in red is going to be the dynamics. And if you actually just sit down and you work out what it is, it gives you precisely these equations that are appearing on the right. And so this is the general procedure by which we compose these systems. And that looks complicated, so let me redraw it with notation. So now remember that I have this special notation for these left-right maps. Remember, we have the exposed variables going forward, and then we have the dynamics, or the so-called update, going backwards. And now we've packaged our coupling law into this wiring diagram, right? That wiring diagram determines one of these forward passes. Namely, it tells you how you're supposed to take the inner outputs or the inner observations and pass them on to be outer observations. And then how you're supposed to take the inner observations and the outer inputs or parameters and pass them into the inner parameters. So that's what C and C# there are doing. C is telling you how you're supposed to pass the inner observations to the outer observations, and C# tells you how to take both the inner observations and the outer parameters and set the inner parameters by them. When you take the composition here, which the composition is that pullback I just defined above, but it's also known as lens composition. It turns out to be equivalent to. That composite system is the coupled system according to that coupling law. So we see that coupling of dynamical systems is given by lens composition, and this is an observation due to David Spivak. So David also, yes.
I have a quick question. So lenses, what does lens mean here?
I'm going to define it on just now. So I mean it
Okay.
in some very bizarre way that comes from computer science ultimately.
Okay.
But by lens, I mean precisely this. If you have a Cartesian fibration, so a Grothendieck fibration, then you can take the fiber-wise opposite of it, and the total space of that fiber-wise opposite is known as the category of lenses. And this is they're these sort of bidirectional maps, and they look like this. They're a pair. That fiber-wise opposite can always be constructed in this way. It's a span in E, whose left leg is vertical, namely, which is to say that it lives in the fibration over an identity, and the right leg is Cartesian, meaning that it satisfies the universal property of a Cartesian lift with respect to this fibration. So why are these called lenses? Well, lenses originate well, okay, I've lost my light in this room. Lenses originate in computer science as a way of solving the view update problem, and they were originally I'm forgetting the actual names of everyone involved, but they were originally developed to solve the view update problem, and they were originally given with a lot of laws. And those laws, so these end up being called lawful lenses. Those laws are sort of an algebraic theory of product projection. So it's a pair of sets together with a few operations satisfying equations, which imply that one of those sets is a product of the other set with some factor. And this is used as an axiomatization of the rules of how you can update fields in a shared data structure. And that was how it was used, the so-called view update problem. So we can see that liminally here. These correspond, these are David Spivak's generalization of lenses, but they correspond to, in computer science terminology, to something that you would call dependent polymorphic lenses. And so they have this pass forward C and this pass back C sharp. And you think of C as the view and C sharp as the update. And that is how we were using it for systems, right? You can view a system by looking at its exposed variables, and you can update a system by pushing forward along its dynamics. And so this is the sense in which systems use the notion of lens coming from computer science. But by lens, I will always mean exactly this. It's a span like this, vertical Cartesian. It's not obvious, but it is essentially the universal property of Cartesian maps with respect to fibrations, that they always emit pullbacks along vertical maps. So in fact, you do compose these spans just like normal spans by taking pullback, even though we don't have to assume anything about E or B, except that E is fibered over B to do this. And then, so I'm going to make it a definition in addition to this, which is that the one extra ingredient we need in order to talk about a system here is the one extra thing in our formula that you can't express just by knowing you have this bundle over here, which is that you need some notion of this fibration, I should say, which is that you need some notion of tangent bundle. So we're going to think of this fibration as saying that E is a category of bundles and B is a category of base spaces. That's how we're going to think of it. And then we're going to equip that with a section, T, which we think of as a tangent bundle. And that lets us define a system as just a lens in the above sense, whose domain is of the form STS, where S is in the base and TS is its image under this section. And so we're going to call the structure of a Grothendieck fibration equipped with a section a tangency. And that is going to be sort of our abstract theory of what it means to be a system. So that's a theory of systems. And one thing I'll note here is that we're always going to consider these systems with their interface. And the interface is the object here. It's the bundle of I over O, which I've written there. I'll always write it there, but it's a choice of a observation space together with over it a choice of bundle of parameters that are valid in a given observation of the system. So in the cases above, just to go back, right? Our systems, you see, these are actually manifolds. These are actually bundles. Our system in these ones on the here are trivial bundles. These ones here are also trivial bundles, but it's really important to think of them as the tangent bundle, right? They just happen to be trivial because R has a trivial tangent bundle. These lenses, as we saw above, if I do this again, are actually these exact kinds of spans, whereas you can see here we have a pullback of bundles, and that makes this a Cartesian morphism of bundles. And here we have a bundle morphism that is over the identity, and that makes it vertical. So these are exactly along this definition of a span where the right leg is Cartesian and the left leg is vertical. And we go into the tangent bundle. So that's what I call a tangency, and we're going to think of these as a theory of systems, or really we're going to think of a symmetric monoidal tangency as a theory of systems, because there's something over here that I also used, which is this product of systems that I haven't covered yet, but we'll get there. And here's some examples. ODEs, as we saw, so if you take submersions as our notion of bundle, living over manifolds, and the tangent bundle is a section of that, then you get this notion of ODEs as the systems for those systems. They compose via lenses. Of course, you don't have to use submersions. You could use vector bundles, but if you do so, you're also committing to saying that your system is parameterized linearly in it. It's linear in its parameters. It's not a linear ODE, but it's linear in its parameters if you make that choice. So changing exactly what tangency you use changes what you mean by system. So it's a giant dial you can turn to say what you really mean by system. So let's see what other places you can turn that dial. If you have any Cartesian category, like say the category of sets, then it comes with a simple fibration, which consists of the product projections. And there's always a section of that which sends every set, let's say, to its product with itself, projecting down via one factor. So it sends itself, its tangent space, you think of it is itself, that says that sort of, in this case, what are the possible changes you could make to a state? Well, you could just jump to any other state, right? That's sort of what Tx equals x means in this case. And so a system for this is what is known in the computer science literature as a Moore machine. It's exactly a Moore machine with input alphabet I and output alphabet O. And similarly, if we have any notion of measurable space, and by this I could mean literally measurable space, but I could mean something nicer like a Polish space, or it could be something nicer yet like a quasi-Borel space, or all sorts of different things on which we have a notion of probability monad. So for measurable spaces, this is famously the Giry monad, but there's probability monads on a gazillion things. You could take sets, for example, with finitely supported distributions as your spaces, whatever you want. You could even addend the monad to have a notion of reward with it, if you wanted to. And if you take systems with respect to this, you'll get a notion of partially observable Markov decision process. In here, the names for I and O, so for ODEs, I was parameter space and O was observation space. In Moore machines, you called them input alphabet and output alphabet. And in partially observable Markov decision processes, you call I the action menu and O the observation space. But in all cases, they have the same essential form. And they all composed by lenses, which, as we saw, could be computed from wiring diagrams. And they in fact, I'm not going to talk about it here, but they can be computed very nicely. You can define the wiring diagrams to be precisely the lenses in the simple fibrations associated to freely generated Cartesian categories. So there's a very nice that description gives you a very nice combinatorial description of the wiring diagrams. Okay, so we're going to start to lift off in this talk now. We have a two category of these tangencies. So I'm going to write just what the one morphisms are here. They're colacs in the tangent bundle functor, and this two category is Cartesian. So it makes sense to define symmetric monodal objects internal to it. And what those are by a theorem that I'm going to use like air here, which is the symmetry of internalization due to Arcor, Bork, and Co. in their recent wonderful paper on F sketches. Which I'm just going to use like air, but it lets you flip around it lets you understand algebraic structures in two categories. So a symmetric monodal object in the two category of tangencies is going to be the same thing as a symmetric monodal fibration in the sense of Moeller and Vasilakopoulou with a lax monodal section. So that's just both E and B are symmetric monodal. The fibration itself is strict, and the section is lax monodal. I'm going to define a systems theory to be a symmetric monodal object of tangency. So that's a symmetric monodal fibration with a lax monodal section. And the reason for that is that we really need to be able to combine our systems with the parallel product before composing them. So let me show you how we get a module of systems out of this. So we're going to think of the category of E lenses. As we saw, a cup E lens can act as a coupling law. So a lens can act as a coupling law, and it couples our systems by acting on them through composition on the right. So that gives us a right module. of the category of lenses, which we can represent as a functor. It sends the interface to the set of all systems with that interface, and it acts by postcomposition. And that functor is lax monoidal whenever the tangency involved is itself symmetric monoidal. And this is the lax monoidal thing is first you take two systems, one with interface IO, one with interface I prime O prime. You then tensor them to get this thing here. And then you use the fact that T was lax monoidal to put that into the correct form, because this one actually lands in TS, tensor TS prime, doesn't land in a T of something, and you need systems to land in T of something. This is sort of invisible in the case of ODEs, because T in that case is actually Cartesian. So I'll sometimes talk about Cartesian tangencies. The tangent bundle is a Cartesian tangency. The underlying monoidal product is Cartesian, and the tangent bundle functor preserves the Cartesian product. The tangent space of a Cartesian product is just a product of the tangent spaces. So anyway, so this is where we get our module of systems, but we've missed something in this story. So this recovers in great generality some of the observations made by David Spivak and his collaborators. Indeed, we'll recover more of that later on. I think I'll mention. We'll recover, in particular, we're going to recover in great generality some of the results of Schultz, Spivak, and Vasilakopoulou in their wonderful paper, Dynamical Systems and Sheaves. So, okay. So what we're missing here, oh, sorry, I should say this. We're going to think about this functor as a symmetric monoidal right module over the lenses. So we think of the lens category as acting on systems here. And I've written down what that means in terms of spans down below, but it's not so important to know that. The point is that the lenses act on systems on the right by composition, and it's in a way that respects the symmetric monoidal product of systems. Okay, so now what we've missed in this whole story is maps between systems. So now we're going to come to maps. And maps are really important in systems theory because maps from simple systems are motifs. They are figures in our systems that are of a special importance. They govern certain kinds of dynamics. So in particular, trajectories, steady states, periodic orbits, all of those are maps of ODEs into whatever ODE you're studying. There's also another class of systems, of maps that's very important, namely maps out of your system into some simple fixed system. Those include Lyapunov and control barrier functions. So I don't have time to go into that now, but it's actually a point of view that works quite well and gives us another important reason to look at the maps between systems, because we want to understand stability and safety and Leibniz properties of systems, and those can be studied through the existence of Lyapunov and control barrier functions, which can be represented as maps of systems. So that, and also model abstraction or refinement or model surrogacy, those all are names for maps between systems, like homomorphisms of systems. So we really need to keep track of the maps between systems, and ideally we would like to understand how the behaviors and safety properties of coupled systems can be understood in terms of their component systems. So we want functoriality for maps, not just to include sort of the normal composition of maps, like post-composition of maps or pre-composition of maps, but actually also to understand the lens composition that we were using as well. So let's just look at an example of a map here. So if we suppose we have an ODE UE, as I mentioned, U is the dynamics. It goes from the state space S together with the parameters I into the tangent bundle of S. And suppose we have a choice of parameters. With that, we can actually for all time. With that, we actually now get an explicit differential equation. We actually fixed our parameters. So now we actually get a section of the tangent bundle, and we can actually ask for solutions. You can't ask for solutions of an ODE until you actually say what your parameters are. So first you choose your parameters. It's also worth noting that the choice of parameters is a map to I, but the general situation we found ourselves in is that we really should have think of the parameters as bundled over the observations. And this is not obvious in the original examples I gave, but if you might imagine a drone is a system where it might have an orientation in space. So the observation of its state space might be its orientation in space. And one of the parameters to that system might be a force that's acting upon it by, say, wind. And that parameter would need to be expressed in coordinates that are relative to the orientation of the drone in space. I mean, it would be natural to, and that would make the parameter space the tangent bundle of the two-sphere, and that is bundled over the observation space, which is its orientation, say in the two-sphere. So there are examples you might have where the parameter space should naturally be seen as bundled, and that's what our sort of abstract nonsense that I just went through suggested as well. So if we're choosing a bunch of parameters, we're also really should be implicitly choosing a bunch of exposed variables that we expect to see. And so I'll add that in, and together P and O here I call the chart of the map. And so we can bundle the data of the solution S into together with P and O into a single diagram, which you see here on the bottom. So it looks like there are a lot more maps, but you see P, O, and S appear here. Everything else is determined. So TS is the tangent bundle functor applied to S, which actually is the derivative, the time derivative of S as a tangent vector. This P bar here, so this middle function has to be S because this bottom square has to commute. So I say, and these are both identities, so it just has to be S. And then this one here is an extra condition that this is a pullback back here, and I want P to live over O, right? And so I want, moreover, that whatever S is, it should be a solution with respect to whatever observations I chose so that my parameters that I'm choosing are well typed for it. And so I need the parameters to actually lift to this pullback. So that's a condition on it, but it's a property, not a structure. So the actual bits of data we have here are P, O, and S. It assembles into this whole diagram, and I can write this on the other side as this kind of commuting square. But note that the edges of this square are of two different kinds. Like the vertical ones, both the maps go forward. You can see they both go forward, whereas the horizontal ones, they go back and forth, and those correspond to our spans. And now it should be quite familiar if you've seen double categories before that this is a double category of spans. So this is a very natural extension to double categories. This is just a double category of spans. And of course, we already saw that the spans involved were called lenses. So this gives us a double category of lenses associated to fibration. So in particular, we have a fibration, we get a double category of lenses. And just to remind you, they're not all spans. It's just the spans whose left leg is vertical and whose right leg is Cartesian. Yeah, so now I want to point out that this construction, which takes a fibration and produces its double category of lenses, is not just two-functorial, which it is, but it also preserves Cartesian products. And the real nice way to see this is that there's a great two-functorial construction of the span understanding of the span construction. In fact, they do it for infinity categories, but it's easily decategorified due to I actually think that it's not Chu and Haugseng. I think that I'm misremembering this. It is Haugseng, but I think it's different authors. I apologize. I think Chu and Haugseng is their algebraic pattern paper, which actually comes up at a different point in this story. So I apologize for that, but it is Haugseng et al. Define an adequate triple to be essentially the data on a category you need to perform this span construction. So you need some kind of maps you can put on the left leg of your span, some kind of maps you can put on the right leg of your span. You need them to have pullbacks along each other, and you need them to be closed under composition so that when you take the resulting span, you get things that are back in the left class and right class. And so from that definition, you can see that if we take a fibration and we put the vertical Cartesian, the left legs to be vertical, the right legs to be Cartesian, that gives us an adequate triple. That's sort of very simple to prove is two-functorial. The span construction on adequate triples is two-functorial, so we get this composite here is two-functorial. It's also easy to show that these preserve products because at all points the products in these two categories are computed in cat. They're just pairs. So as a result, it also preserves symmetric monoidal objects. And so we get a two functor that takes a symmetric monodal fibration and produces a symmetric monodal double category of lenses, which is rather nice. Okay, so now we're going to try to construct loose right modules of the double categories of systems. So we saw that a right module of a category gave us the notion of the compositionality of systems by lenses acting on from the right. But now the lenses are the loose morphisms in our double category of lenses, as opposed to the tight morphisms, which go vertical. So loose in my talk now will go horizontal, tight will go vertical. That's different than the conventions for Perret, but it follows the conventions of, for example, Evan Patterson and a number of other people. So it's like the Topos Institute conventions are this way. So there you go. It differs from the conventions of my monograph, which you might find on my website about this stuff. Apologies. But it's better this way for, well, the conventions are arbitrary, but the conventions I'm using in this talk are better than the one in the monograph. Excuse me. I'm running out of time. So it's not clear what a loose right module even means. As far as I can tell, this hasn't actually been written up in the double category literature yet. So there's an evident generalization we could try, right? We know that a right module of categories is a functor into sets. We might think maybe it's some kind of double functor or lax double functor into span set. And this is a kind of module of a double category. It was defined by Perret, and Perret gave a representability theory for double categories that produce these kinds of lax functors. But these are really the tight modules. So they are acted upon in the tight direction, which is to say vertical composition. That's not what we want. We want our action of our systems to be by lenses, and lenses are in the spanny direction, which is in the loose direction. So that's not what we want. So we could transpose our systems, and this is what I do in my monograph. But that only works if you have a strict double category, and it does turn out that you have a natural strict choice for your if your fibration is split, then the double category of lenses is naturally strict. But this general story for compositionality of systems as symmetric monodal loose right modules works for example, structured cospan and decorated cospan approaches to systems due to Jaz Myers and his many collaborators. That truly give you weak double categories, so you can't do this trick. So instead, there's two real ways to define them. There's, I would say, four ways to define loose modules. Like there's going to be, you could give the right notion of sort of pseudo functor that would be from the transpose into span set on a correct like weak double category, and that's been written up on the Topos Institute blog by Evan Patterson. You could give a notion of loose fibration for double categories, which I know is in the work by Evan Patterson, Michael Lambert, and I, where we're aiming to give that. It's mostly Michael writing that up or doing that. However, we need the whole two category, and we need it fast. So there's actually two good choices for how to do this. The really slick, easy choice, the fastest choice, is to use double barrels, because the double barrel two category is just a slice over the walking loose arrow. So I'm going to explain this on the next page. But it is true that you could also define them to be pseudo bimodules between pseudo categories. And this is sort of the most natural definition. And you can give a very concrete definition of this, and you can actually prove them equivalent, which is going to be coming up in a forthcoming paper where Sophie, Jason, Kevin, and I work out the fundamental theory of these loose bimodules, and we prove the equivalence of these two points of view, and then we develop the rest of the stuff I'm going to talk about now. So a double Joyal defines a barrel to be a functor into the walking arrow, which is the category just having a single non-trivial arrow. And he shows that they're equivalent to bimodules of categories. And we can do the same thing for double categories. The walking loose arrow now, I've written it up as a double category here with all of its identities, just so you can see that there's actually more going on than just one loose arrow in it. And in fact, you see that there's actually, a lot of structure. And over zero, we have identity loose arrows, identity tight arrows, and identity square. So over zero, somehow there can live an entire double category. Over one, there can live an entire double category. And over two, the loose arrow itself, there can live sets of things, but two has an identity arrow, so there can actually live a whole category. And what we will see is that a loose bimodule is just a double category with a map to it. So you think of it's a double category that's labeled by, am I in the right? Or sorry, am I in the left? In which case I'm labeled by 0. Am I in the right? In which case I'm labeled by 1. Or am I part of the bimodule itself? In which case I'm labeled by 2. And it's going to be a loose right module if the part labeled by 0 is trivial. So, we sort of have a dummy source for our things in our modules that not in addition to the target that can be acted upon. But that's it. And because the top of this thing is a full double category, you can compose arbitrarily in it, and it just has the composition by functoriality of the projection to the loose arrow, or the labeling function, has to preserve those labels. And that says that if you act by something labeled by 2, by something labeled by the identity of 1, you get something labeled by 2 because this was an identity. And that says that you can act on the right on the things that are modules in the module. Okay. So I'm going to try and close up here. But so now we actually need to construct some of these. So the first construction to note that's really easy if you're using double barrels is to define the Hom bimodule of D. And that's just the product projection. So if you run through what that is it has a copy of D sitting over 0. It has a copy of D sitting over 1. And over the loose arrow itself, which is called 2, it has every loose arrow in D, because that's what gets paired with the single loose arrow here in the product. So that's a wonderfully simple construction. It's obviously two functorial, and it preserves Cartesian products, meaning it also preserves symmetric monoidal objects, meaning that if you have a symmetric monoidal double category, it has a symmetric monoidal loose bimodule of its Hom, right? And so what we're going to do is just restrict these Homs, because remember, a system is just a special kind of lens, and a lens is a special kind of loose morphism in our double category of lenses. So it suffices to just restrict the loose bimodule, the loose Hom bimodule of lenses to those whose left form is of the form ST to the S, or STS, the tangent bundle. So restriction here works like it does. I'm not going to go into it because this is actually a fairly involved theorem. Like it's fairly involved by hand construction, as far as I can tell. It should follow from abstract nonsense, but not at the level of strictness we need. So, if you take a niche, by which I mean a bimodule, which I'm writing here in the bimodule formalism, as if we had a double category of double categories and loose bimodules, which I'm not claiming, but this is just notation. For a bimodule together with a double functor, a pseudo double functor into its domain, and a pseudo double functor into its codomain, we can restrict them. And intuitively what it does is it's just like restricting a bimodule. This is a restriction of scalars, if you will, for bimodules here. But the trick is showing that this restriction preserves symmetric monoidal structure, because remember, we want to construct symmetric monoidal loose right modules, because we don't just care about acting on the right by coupling laws of our systems. We also have to take the parallel product of our systems first, which is the symmetric monoidal product. So the way we do that is by expressing a very tricksy functoriality, or two functoriality, really, or pseudo-functoriality, really, of this restriction functor, and I've sort of expressed it here. The way we do it is we define the correct notion of morphism of these niches to be, well, you have a niche up front here, you have this niche in the back here, whoa, stretched out, and then you have these collax commuting squares inside, where this is a tight transformation. These are both tight transformations, but on the left, you ask that it be that it have a conjoint pro-transformation. And so that we call that a conjoint commuter transformation, because it has to satisfy the commuter cell condition that Perret named in one of his papers. I think it's a retrocells paper, but I'm not sure. And on the right-hand side, we need it to be a companion. And the reason for that is if you have an M of the form from F naught D or F naught prime D to F1 prime E, so this is in the back here, and you want to apply this map of morphism of bimodules that it takes place in the bottom of the niche here. Well, what you get here is something of this form, right? You get something that goes from G naught F prime D to G1 F1 prime E, and that's just because this bottom square is sort of a morphism. This is just what it means to be a morphism. And by the way, a morphism of bimodules formally in the double barrel point of view is a map in the slice double category. So it's just a double functor on the whole top of that thing that preserves the labeling. But that's not of the right form, because that's not of the form of the restriction. A thing in the restriction has to go between something of the form F naught and to something of the form F1. So what we do is we just take the conjoint of the first cell here and the companion of the first cell there. And that actually, I don't know if I wrote it up. Yeah. So that actually appears in the definition of the symmetric monoidal product of. So now, as a corollary of the fact that we have this Cartesian pseudo-functor here, which, by the way, not easy. That's where half the work is here. Is that when you restrict a symmetric monoidal loose-right module along lax-symmetric monoidal pseudo-functors, whose unitars and laxators are conjoint or companion commuter transformations, depending on whether they're on the left or the right, then you get a symmetric monoidal loose-right module. And the actual construction is that if you take the symmetric monoidal product of two things, right, the product in there, excuse me, this is there should be F naught and F1 on both of these. It's a typo. They're in the restriction. You take their product. Well, the product of them does not go of the correct form. It's not in the restriction. But again, we have these like laxators here that we can put on either side. And if you really remember all the way back, this form of composition actually already appeared in this. It is the one that sort of correctly rejiggles a map into the tensor product of tangent spaces into a map into the tangent space of tensor products. Okay. So that gives us the correct thing. And from that, we can then actually put together a big ol' the two functors, so long I couldn't fit it on one line, which takes the tangency, turns it into a map between adequate triples, where here in the back, we do this fun trick that if you take any category, you can give it an adequate triple structure where both classes are just the identity. When you take spans in that, you're asking for a double category, whose tight direction is the same as your ordinary category, and whose loose direction are spans, where the left leg is an identity and the right leg is an identity, which does nothing. So you end up with just B considered as a loosely discrete double category. And so we end up with this map from B into lens, which is just a tangent bundle. Again, we can restrict the Hom of the tangent bundle, the Hom of the lens construction by that to get a loose bimodule that is a loose bimodule that is of the form lens E mapping out of the tangent space into something. And that is exactly what systems were. They're lenses that map out of the tangent space, the tangent bundles into interfaces. And then this is a bimodule, but if we just forget about the action on the left, just completely forget about the action on the left, you get a right module. And that's the right symmetric monoidal right module of systems. It's two functorial, as you can see in tangencies. All of these two functors are Cartesian. So it gives us a map from symmetric monoidal tangencies to symmetric monoidal loose right modules. And that takes what I call the systems theory and produces this symmetric monoidal loose right module, which governs the compositionality of systems in that theory as they compose via coupling laws. So I'm just about done. So I think I'll just say here that of course you could, if you take in, instead of a tangency, you take in something like a category with finite limits, you can get spans where you've restricted the Hom to spans out of the point. And this gives you something that really looks like Jan Willem style behavioral control theory. And these give you things that appear in the dynamical systems and sheaves as the Schultz, Spivak, Vasilakopoulou paper as the target of their behavior functor, which I'll come to shortly, very quickly. And then if you put in a category of finite colimits, you get something that gives a nice formalism for the structured co-span approach to composing systems. And of course, you could, instead of starting with Rex, you could start with the decoration data due to Brendan Fong and the various people who have developed that, including Patterson and Kenny Corser, who have developed that to various degrees. So, okay, as a final thing, I just want to gesture at the Yoneda theory of systems theory. I think for reasons of time, I'll skip over this theorem, even though I'm quite happy with it. It's a way of lifting discrete op vibration classifiers. So this is a theorem that tells you that span set classifies strict discrete op vibrations in double categories and lax functors, which originally is due to Perret, but it comes out of abstract nonsense. But we can use it to show that spans set, the module acted upon by span set via pullback of spans out of the single point, classifies strict discrete op vibrations in symmetric monoidal loose right modules. And in particular, what this means is that if you have any, say, subcategory of quote unquote clocks in your systems, right, then you get a lax morphism into spans of sheaves on those clocks. And we call this the temporal sheaf of behaviors. And this does recover Schultz, Spivak, Vasilakopoulou example there, but it does it for any system series. So in joint work with Owen Lynch, Sam Staton, and Igor Richel, we have done this for POMDPs. And in that, so clocks for ODEs are just they're just open intervals in the real line equipped with the differential equation dt equals 1, saying that time flows at unit rate. Mapping out of that gives you solutions of length, well, b minus a, and they assemble into a sheaf that Schultz, Spivak, and Vasilakopoulou called the behavior sheaf, and they land in the category of sheaves on intervals in R, which was called the temporal topos by Schultz and Spivak in their book Temporal Type Theory. For POMDPs, instead, we get a notion of clock that depends on a choice of standard Borel space, so a choice of sample space together with a probability distribution. The clock there sort of updates deterministically in time and then independently in the sample space. So you resample independently, and it represents as maps out of it random variables, sequences of random variables evolving according to the law of the Markov decision process. And the natural variation of this lands in Simpson's topos of random sets. So we get this nice notion of temporality for POMDPs, where temporality is learning more about our probability distribution in the sense of going by finer and finer or coarser and coarser in a filtration, I think, or finer and finer, if I think that through. I'm well done. So thank you very much.